Good afternoon.
Afternoon.
Can you link the poll?
Sure. Okay. So we're going to continue the practice questions from yesterday. So in this perfectly closed ideal system, your total energy remains the same. Good, 66% of you. So your total energy never, again, your energy cannot be created or destroyed, right? You cannot create energy or destroy energy. You can only transfer energy. So your total energy in a system, no matter what, is going to stay the same. You can see that in every single phase and every single image that you have a total of 4 shapes. You have 4 shapes here. You have 4 shapes here. 4 shapes. 4 shapes. So no matter where this pendulum is, its total energy is conserved. No matter where it is. No matter where it is. If you can't create or destroy it, how does it exist? Well, there's already energy here, right? For example, you have chemical energy in the bonds of what you eat, right? And you store that in fats. No, this is not the attendance pool. This gravitational potential energy comes from the force due to gravity. right? And if you think of gravity in the 4D, 4 dimensions, if you think of gravity acting in a 4 dimensional space, well, gravity is kind of like a well, but that's only potential energy due to gravity. Chemical energy is also another form of energy, right? It's in your food, it's in the bonds between atoms, right? And your body breaks down those bonds, and when those bonds break, there's energy in those. So the energy was always there. The energy was always there since the beginning of the universe. And since the beginning of the universe, the only thing that has happened is that the energy is just converted into something else, right? Energy can only be converted into other different forms. So I want to draw us back to what happens here. Oh, she just drops down. Okay. Anyway, so at this point, let's actually increase her mass. Yeah, sure, why not? Let's increase the amount of gravity too. All right. So this skateboard is on this ramp, falls down this ramp, right? So you have a total amount of energy. You have a total amount of energy, and your total amount of energy is equal to your potential energy at the top. So you have a lot of potential energy here, but you don't have much kinetic energy because, again, kinetic energy is 1/2 mv squared. And if you're not moving, well, you don't really have kinetic energy. If your velocity is 0, you don't have kinetic energy at all. So what happens after I play this simulation as the skateboarder falls down this ramp or slides down the ramp? I think I showed you this in the simulation yesterday. Really? No one. No one remembered anything we did yesterday. Disappointing.
The potential energy decreases.
The potential energy decreases, okay, but
Sorry,
does
my
that go?
brothers are yelling. It goes into the kinetic, so the kinetic increases as the potential decreases.
Yeah.
As you get like closer to the floor, like to the ground, but the total energy stays the same.
Yeah, that's correct. Your total energy stays the same. Your total energy stays the same. The only thing that happens is that your energy gets converted. And so as a skateboard is going down this ramp and up this ramp, you see that the potential energy and the kinetic energy are both converting into one another. And so once you reach the bottom of the ramp, once you reach the bottom of this ramp, you see that most of the potential energy, and let's just pretend that, let's actually pretend that there's no potential energy here. Let's pretend that this little bar here doesn't exist. All this potential energy has now transformed into kinetic energy. And so that all that available gravitational, all that available potential energy due to your force due to gravity has now turned into kinetic energy, the energy of motion. So let's think about this. My total energy stays the same, right? So if you were to add up basically your total energy, yeah, sure, why not? Let's say your total energy is equal to your potential energy plus your kinetic energy combined. So let me just give, I don't know. Actually want less gravity. Oh, right. So let's pretend that my total energy here, let's say my total energy is 100 joules. Right? That's how much energy there is in this skateboard ramp system. So only in this very confined system between the skateboarder and the ramp, the total energy of both, if we're just looking at this ramp and this skateboard, let's just say my total energy is 100 joules. And well, the person hasn't moved yet, right? So the person hasn't moved yet. So her initial velocity is 0. So she has all of her energy is in potential energy. All of that energy is in potential energy. So, well, now we let go, right? And let me just pause at this point. So, but now her potential energy decreases, right? Because now she's sliding down a ramp and she has some sort of velocity that's not 0. Let's just make up some numbers. Let's say now her potential energy at this point in time, let's say her potential energy is 66 joules. What would be a reasonable kinetic energy here? If your total energy would be 100 joules and your potential energy here is 66 joules, what would my kinetic energy be? Tell me my... Good. Yeah. Well, it's going to be somewhere around 33, 34 joules, right? So we want it to be 34 joules. I can see why you thought it would be 33 because like you saw that this green bar was like half of this and then you thought like 33 joules, which is fine. I can see why you thought it was 33. But if you're taking it out of a total of energy of 100 joules, well then if your potential energy is 66 joules, then your kinetic energy must be 34 joules. Your total energy remains the same. This entire universe, there is a set amount of energy in this entire universe. And that energy has since been spread since the beginning of time. Whatever your beginning of time is, whatever you think the beginning of time is, your energy has only been spread out from that beginning period. So let's actually go through with the simulation even further. What now? What do you think would be an ideal? What do you think my energies here are? Someone just it's fine. Just make up a hypothetical, some hypothetical energies that makes sense.
kinetic it could be 60 and potential could be 40.
Yeah. Your kinetic energy here could be 60 joules, and your potential energy of the skateboarder down here could be 40 joules. It definitely can make sense. Your total energy here is still 100 joules. When you add up both of these energies, you still get 100. Your energy, it's just, this energy is not going nowhere. The energy here is just being converted into another form. And then you reach all the way to the bottom, right? And let's pretend that this bar doesn't exist. All right, let's pretend this bar doesn't exist at all. Yeah, no worries. Yeah, let's pretend this bar doesn't exist. So when she reaches the bottommost point, her kinetic energy is now 100 joules and her potential energy is 0. So no matter where you are, your total energy must add up to 100 in this system. In this very specific scenario where there is no friction, my total energy must be 100. No matter where I go, in this scenario only. So no matter where the skateboarder is, your total energy is 100. Which is where this formula comes in, guys. Your total energy is equal to your potential energy plus your kinetic energy. Are there any questions? I make sure you do ask questions. Again, if you don't understand this, please raise your hand. Okay. So hopefully you guys get the logic here, right? So no matter where you are, your total energy must remain constant. The only thing that changes are your kinetic and potential energies. So let's do some more practice problems, right? Let us do more practice problems. What are my knowns? Give me my knowns.
The mass is 22 kg.
20 kg. What else?
The height is 10 meters.
Height is 10 meters. So your height here is 10 meters. And what are you trying to find out, guys?
The kinetic energy.
The kinetic energy. And so I'm actually going to use, yeah, sure, why not? Can we be more specific with that, though? Be very specific.
The lowest kinetic energy?
The lowest kinetic energy. Okay, at what position? Top or bottom?
Would that be the bottom because it's the lowest?
Oh
wait, no, potential's
no.
Okay,
Where are you
it
getting
would
the
be at the
lowest from
top.
again?
Where it says minimum.
Minimum.
So would it be at the
So
top?
okay, so it's kind of like the static friction thing, where if you have any force over the required force to move an object, you'll move it. It doesn't matter what force you are, as long as you're over it. This is essentially saying the same thing. You can get this cart over this hill if you exert 1,000,000 joules, right? If this cart has a kinetic energy of 1,000,000 joules, it'll definitely go over this hill, no matter what. But this minimum right here, what they mean by minimum, they just mean like what is like the least amount of energy you need to put to actually get this cart to the top of this hill. That's what they mean. So they actually want the kinetic energy at the bottom. What is the kinetic energy required to get this cart to move and reach the top of this hill? What is the minimum? Otherwise, it's probably just gonna, if you don't exert at least the minimum, it might just stop here at like some point here and then just fall back down again, which is something you don't want to do. And the clue here is, what is the minimum kinetic energy of the cart in the position shown? So this is the position. It's at the bottom. So they want to know the kinetic energy. Again, you can't really solve it using Ke is 1/2 mv squared. You can't really do that. Can't really do that at all. Because we don't know what the velocity is. Can we find out what our velocity is? For sure. We can definitely figure out what our velocity is. But what to do with the using conservation of energy? So the first thing you guys have to realize is that, well, at the bottom, you have a height of 0, right? So the car is at the bottom and you have a height of 0. Your total energy at the bottom is equal to your potential energy at the bottom plus your kinetic energy at the bottom. What is my potential energy at the bottom and why? Someone, please help
The
me.
height at the potential energy would be 0 since it's at the bottom, and the mass would be 20.
Yeah, your potential energy would be 0. Wait, what did you say your kinetic energy was?
I didn't say kinetic, I just said
Okay.
potential energy.
Okay. Yeah, your potential energy at the bottom would be 0 because your height is 0. Anything multiplied by 0 gives you 0. So no matter what your mass or your acceleration due to gravity is, as if your height is 0, you don't have any energy. You don't have any potential energy. The force due to gravity cannot pull you down even further. There is no potential for the force due to gravity to pull you down. The ground is right underneath you. So unless somehow there's a sinkhole, you're not going down further. Zero. I'm actually going to erase the 0 just for convenience because I don't want to write even more. So your total energy is going to equal to your kinetic energy at the bottom. So we figured that out. We figured this out. So what is our total energy then? Well, there's a way to find out what our total energy is by solving for our total energy at the top. So once the cart is at the top, it has a certain amount of potential energy. And we know that my entire potential energy, my potential energy at the top, plus my kinetic energy at the top is equal to my total energy. Let's assume that once the cart hits the top, my velocity is 0. My cart stops completely once it hits the top, right? If the cart stops completely after it hits the top, what's my kinetic energy?
0.
0, right? Because your velocity is 0. Remember, the formula for kinetic energy is mv 1/2 mv squared. If your velocity is 0 at the top, that entire thing right there is 0. So mass is 20, 9.8, 10, h is 10.
It would be
plus
1,960.
1,960. Okay, good. So now this is your total energy. Your total energy, no matter where this card is, if this card is over here, the total energy of this card over here in the middle would be 1960 joules. Yeah. And so if you know that your total energy is 1960 joules, well, your kinetic energy at the bottom is going to be the same exact thing, right? It's going to be the same exact thing. So your kinetic energy at the bottom is 1960 joules. Questions? So there are a few things, there's a few assumptions and logic you have to make here, right? So the first kind of logic is that your total energy is always the same. In a scenario, your total energy does not change. It can only be converted into one form or another. Let me know if you need more time to copy this down. I'm going to close this. I'm going to erase the work in like what, 10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay. This is your attendance question. What's the link in chat? You have like a minute, okay? You have a minute. I think, when I was driving home yesterday from John Adams High School, I noticed something. It's like a weird contrast. When I was driving home from John Adams High School yesterday, I was looking at people on the sidewalks, and as I was driving past, most of them did not have masks on. I see like this teenage girl just walking past, acting like it's summertime. I see this old lady that has that's using a cart in front of her, and she's using it as like a crutch to walk. She didn't have a mask on. Another guy had his mask on, covering his neck and his chin, so protecting his neck and chin. I don't. That was like the first time I've ever seen like so many people not wearing masks. It's very different from what I'm used to seeing. All right. Good. So energy cannot be created, right? Cannot be destroyed, cannot be created. So the statement is false. The statement is saying energy can be created and destroyed. It's completely false. The energy is finite. I mean, it's a set amount, not finite. It's a set amount ever since the universe was created. I marked you here. Whoever said they couldn't answer. So there's a reason we needed to do that a really long about way. I'm going to teach you guys a shortcut now that you can use for this homework only. It doesn't really work for various situations because we deal with very ideal problems. The long way I've been doing it is the correct way. That's the way you usually want to do it. But I'll teach you a shortcut. So the mass of this ball is 10 kg. You have a ball that's dropped. And just before striking the ground, the ball reaches a velocity of 20 meters per second. So I'm just going to say the final velocity of this ball is 20 meters per second. The question also then asks you, what is your gravitational potential energy relative to the ground at the instant it was dropped? So they want to know what the potential energy of the ball is right as it was dropped. So they want the top. They want their potential energy at the top. And here's a shortcut to solving these type of problems. I'm going to drop this person. Wait, Hashi, I want to see something. Okay, that's what happens. Okay. Actually, I'm going to put it over here. So the problem gives you your final velocity. The problem gives you your velocity at the bottom. Just before you hit the ground, they give you velocity, which means you can calculate what your kinetic energy at the bottom is. You can fully calculate your kinetic energy at the bottom because you know that the formula for kinetic energy is 1/2 mv squared. And let's solve for this kinetic energy. So your kinetic energy at the bottom, just before it hits the ground, your kinetic energy is 2,000 joules. Are there any questions about your kinetic energy at the bottom? Any questions at all? Please raise your hand. Okay. What do you guys think is going to happen to the skateboarder's potential energy when she reaches the top? Let's say this person's kinetic energy. Let's say this person's kinetic energy right now is 2,000 joules. What is her potential energy going to be when she reaches the top?
2,000 joules.
Yeah, it's going to be 2,000 joules. All her energy has now transferred into potential energy. And so here's a shortcut, right? When you understand this concept, the concept here is that all your energy has now been transformed completely into potential energy. So that's a shortcut here, right? The concept you need to understand is that if you are falling from a certain height, once you reach the bottom, I couldn't time it correctly. You learn what the oranging means tomorrow. It's falling too fast. Okay, now I'm pissed. Whatever, that's fine, it's good enough. Once you hit the ground, all your energy that was in potential energy has now been transferred into kinetic. Well, just before it hits the ground, just before. So that's the shortcut, right? That is the shortcut. That is the shortcut. So if you know that when you hit the ground, your kinetic energy at the bottom is 2,000 joules. The energy must come from somewhere. Where did the energy come from? The energy came from the potential energy at the top. And so all that happened was that the potential energy transferred into kinetic energy. That's it. Are there any questions about the answer here, the shortcut? This really only works for the homework, this homework. It doesn't really work for anything else. Also, your question yesterday, where you asked me why I didn't calculate F, why I didn't include G in this formula. Did you mean like, did you think that this G right here was like an actual variable?
No, I was confused on the MGH because I thought like the G was connected to the M for some reason. Because last time we did a problem using weight and you didn't use it, so it stuck to my head that like it was connected. So that's why I asked you. But now I know like it's separate and you have to include it when it's just mass.
Yeah. Good. All right, guys. But yeah, this energy conservation is very important. It's very important for you to understand. If you do have any questions about this, it's really important to ask me, okay? I would say that the conservation of energy is an important part. Take a look at your homework. Question 1. So you have this pendulum, right? You have this pendulum and you can assume where's my height thing? You can assume that your height at your equilibrium position is 0. That's what you can assume. It's fine to assume that. Otherwise, you can just say that for number 1, your change in height is 1.5. It doesn't really matter. Doesn't matter in the end. Whatever you want to do. That's number 1. Number 2, we did this in class yesterday. Actually, we didn't do number 2 in class, but I think you guys can figure it out. Actually, I mean, question 2 wants height. Question 2 wants height. How do you get height? You get it from potential energy. You know that potential energy is MGH, okay? So you're basically solving for potential energy here. Solve for that first. But other than that, it should be fine. It's not too hard, not too difficult. Number 3 is a conceptual question. We talked about this multiple times. We did number 4 in class. You can't do the shortcut for number 4 because the object starts at a height of 3 meters and the object lands. I mean, not lands, but the question is asking for energies at 2 meters. So you can't do the shortcut there. You can do the shortcut for number 5. We did number 5 in class. We did the question number 5 in class. 6 is a concept question, should be fine. 7 we did in class. 8 we also did in class. Guys, if you don't have any more questions, I'll see you guys tomorrow.
Bye. Have a nice day.
Bye.
Have a nice day. Goodbye.
Bye-bye.